In pursuit of transferring technical knowledge and just to gear up the new engineering entrant, myself Pranab is here to deliver today's presentation, Power Transformer, Part 75. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with the electrostatic charging phenomenon in transformer insulation. The electrostatic charging phenomenon is mainly initiated when there is invariably some incidence of happenings as due to have the relative motion between the oil and the surface of the solid insulation. Solid insulations at all the time that are being the stationary part, whereas the transformer oil is designed to have a continuous flow through and around the solid insulation in a transformer. Static electrical charges that are usually be produced within the transformer as and when arising from separation of positive and negative charge at the interface between the following oil and solid insulation. The electrostatic charging phenomenon can also occur during the flow of insulating oil over metallic surfaces associated with component such as supporting framework for holding the winding and core assembly, oil pipelines, oil pumps, etc. Separation and subsequent transfer of positive and negative charges at the solid liquid interface during the flow of oil, which primarily occur as due to have the difference in electron affinity between the oil and the solid materials. To avoid the occurrence of localized hotspots, the insulating oil is compelled to circulate through the cooling ducts in order to have an efficient removal of the heat produced by iron and copper losses. A static electrification is thus to generate as of a subsequent resultant effect of the contact of streaming high resistivity oil and the surface of solid insulation such as pressboard. The accumulation of interfacial space charge in the oil paper insulation system of transformers is being a normal phenomenon and can become a critical issue in the process of insulation aging. Interfacial charge accumulation is primarily caused by the usual differences in electrical permittivity and conductivity of oil and paper, and that leads to allow charge accumulation and localized electric field enhancements. The electrical properties of both oil and solid insulating materials in a transformer are efficiently designed to provide high resistivity and high permittivity. The high resistivity that helps to resist the flow of electric charge and the high permittivity that has met to enable the storage of electrical energy in an electric field rather than allowing charges to dissipate quickly. The condition may have become more vulnerable when these localized field enhancements would touch a critical level where it can create localized areas of intense electric field, leading to nearly exceed the oil's dielectric strength. Partial discharge is a localized breakdown and that can be triggered off once the electric field intensity of a particular stressed zone would have been exceeded the oil's dielectric strength. Over time, these discharges would lead to accelerate degradation and aging of the insulation material, potentially causing a complete failure of the transformer. It is quite evident that whenever there would have a change in oil's dielectric constant, that can change the electrical field distribution within the transformer oil. In an oxidized transformer oil, the oil's conductivity would have to change due to obvious presence of polar molecules as of oxidation products in oil. The oil's conductivity, as it changes, which can lead to a greater difference in conductivity between the oil and the paper, causing to influence greater amount of charge accumulation at the oil-paper interface. However, higher accumulation of interfacial space charge in oil-paper insulation system would rather have to create localized distortions in the electric field, causing the field strength either increasing or decreasing at certain points. If somehow the electric field strength would have been significantly enhanced at a specific location because of charge accumulation, then this particular location has become the most weakest zone in the insulation, most important. So, the electrical field distribution within the transformer oil is also thereby significantly affected by changes in dielectric constant whenever the oil undergoes oxidation reactions. As relates to oxidation reactions in transformer oil, were thus to produce polar molecules like acids and other byproducts. These polar molecules, as produced, would have a separation of electric charge, which means that one end of the molecule is partially positive and the other is partially negative, creating a permanent electric dipole moment. This has happened while a covalent bond would have been formed by the two atoms of having different electronegativity. The atom of higher electronegativity must have the normal tendency to pull the electron density closer to itself, developing a partial negative charge. So, the atom of higher electronegativity would have the greater electron density around that atom. Whereas the atom possessing with lower electronegativity would have a lesser ability to attract electrons, leading to a deficiency in electron density around it and thus to develop a partial positive charge. This shift in electron density would thus to constitute a higher concentration of electrons around the more electronegative atom, resulting in an uneven distribution of electron density that has to create a polar covalent bond. However, during initiation of oxidation process in transformer oil, there would have to create various type of chemical byproducts like peroxides, aldehydes, ketones, alcohols, acids, and sludge. These oxidation as well as hydrolysis byproducts would thus to accumulate at the interface between the oil and the solid insulation. The insoluble byproducts would also to settle at the boundary between the oil and the solid paper or pressboard. The accumulation of ionic byproducts on the surface of an insulator must have to create a charged surface that can distort the local electric field. As the oil and the insulating paper have different conductivities, so that would lead to the accumulation of charges at their interface. The accumulation of ionic byproducts would have been further escalated with the acceleration of solid insulation aging process. However, that would lead to provide a higher concentration of charge carriers in both liquid and solid dielectric materials. Therefore, presence of ionic byproducts, which are essentially of free ions, would thus to contribute to a significant increase in conductivity of the liquid and solid insulations. It is also being noted that once an electric field is applied, ions would have been generated within the insulation material. These ions would then have to migrate and being trapped on the surface of the solid insulation or at the oil paper interface. Trapped ions on the surface of solid insulation or at the oil paper interface would further to intensify the accumulation of charge, leading to distort the local electric field, creating localized regions of higher field strength. This has happened when the ions as present in insulating oil come in contact with charged surface of solid insulation. Then these ions would have been attracted to the charged surface due to impose of electrostatic forces, forming a compact layer of space charge. Now, it is to understand that the solid insulation surface would thereby to develop an electrostatic charge due to various factors such as corona or partial discharge. When the charged surface comes into contact with ions, then there would have to form an electrical double layer which consists of two parts. One, the layer adjacent to the charged surface would have to form a compact layer or stern layer stern layer, as because the counter ions are being tightly held directly to the charged surface by strong electrostatic forces. Again, I repeat. Number one, the layer adjacent to the charged surface would have to form a compact layer or stern layer, as because the counter ions are being tightly held directly to the charged surface by strong electrostatic forces. Number two, beyond this compact layer, there is a region to form which is called diffuse layer when the ions are less tightly bound to a charged surface, that is, rather being kept in more spread out condition. At the diffuse layer region, where the ions are free to move due to both electrostatic attraction forces and their own thermal motion, and by which the ions and the charged surface would have been kept dynamically balanced with each other. In this region, the electrostatic attraction would have the ions to pull towards the charged surface of the solid insulation. while thermal motion has made them to disperse. because, because of these interactions, the concentration of ions in this region are not to be fixed state, but are free to move within the fluid, creating the diffuse layer. The extent of diffuse layer is thus to be determined by the factors which include 1. Number A, temperature, ion concentration, number B, and last one C, ion charge. Oxidation byproducts such as acidic compounds or polar fragments are thus to form due to degradation of transformer oil that would have to accumulate at the interface of oil and solid insulation. The charged degradation products like acidic compounds and other polar substances in oil would have to contain certain ionized groups carrying positive and negative charge. Solid insulations such as cellulose-based paper insulations are inherently made of polar molecules. These polar groups have configured with an uneven distribution of electrons within the molecule, resulting in partial positive and negative charges, a characteristics of polar molecule or dipole. The ionized groups on the oil degradation products are thereby drawn to the oppositely charged polar regions on the paper insulation surface through electrostatic forces. This phenomenon is referred as adsorption, where molecules from the liquid or gas phase accumulate on the solid insulating surface. So, the electrostatic attraction between the ionized oil degradation products and the polar surface of the solid insulation causes the degradation products to accumulate or adsorb on the surfaces of solid insulation. The adsorbed charged molecules or ions directly attached to the solid insulation surface carry a specific charge due to electrostatic interactions, forming an inner stern layer. Forming an inner stern layer, that is composite layer. The charged inner layer then electrostatically attracts the flow of other mobile ions with having the opposite charge, that is counter ions, from the surrounding components of the degraded oil. This counter ion adsorption leads to the formation of more spread out diffuse layer of mobile counter ions. Most important. Due to the presence of oxidative byproducts in transformer oil, there would have to create formation of a distinct diffuse layer at the oil paper interface. The existence diffuse layer is rather to be influenced by both the electrostatic attraction of counter ions towards the surface charge of the paper insulation and the disordering effects as caused by the thermal agitation of these counter ions within the oil, that is thermal movement. However, the random thermal motion, that is thermal agitation of these ions, would thus to move them away from the surface of the inner layer Again, I repeat, however, the random thermal motion, that is thermal agitation of these ions, would thus to move them away from the surface of the inner layer, creating a diffuse region where the electrostatic attraction and thermal energy are in balance. A balance between electrostatic forces and thermal energy is crucial for the stability of the diffuse layer, as because this layer helps to prevent from aggregating the ionized molecules of oxide byproducts in the transformer oil. The kinetic energy of the ions is directly influenced by the thermal energy as induced within the ions, atoms, and molecules. Kinetic energy of the ions is directly influenced by the thermal energy as inducted within the ions, atoms, and molecules. If the thermal energy would have become abnormally high, then as of the resultant effect, there has to create an enhanced random motion of the ions of the oxidative byproducts within the oil. The random motion of the ions once being significantly high, that would cause to get the better of the attractive electrostatic forces which actually hold to bind the ions to the charged surface within the diffuse layer. Such phenomenon where the ions gain enough momentum to escape the electrostatic attraction, leading to diffusion away from the surface. Due to the loss of ordered structure of the diffuse layer that has made the ions to move more freely, leading to increase the local concentration of ions, leading to increase the local concentration of ions. However, higher concentration of ions that would cause to promote attractive surface forces within the ions, making an obvious aggregation of ions. As a result, the ions diffuse away from the surface, leading to certain collapse of the structure as formed by the diffuse layer. On the contrary, if there may have a too strong electrostatic forces, then the ions would be held too rigidly, resulting in an increased electrical conductivity and leading to potential breakdown of the insulating oil. So, the balance of electrostatic forces and thermal energy would thus to maintain stability of the diffuse layer in transformer oil, which ultimately helps to keep these ionized byproducts in a dispersed state and hence to maintain insulating properties of the oil. It is quite evident that the combination of the initially charged surface layer, that is compact stern layer, the diffuse layer of counter ions would thus to create a phenomenon like electric double layer at the oil paper interface. Therefore, acidic compounds and other polar molecules, if present in transformer oil, then that would preferentially adsorb onto the surface of the solid paper insulation, creating an electric double layer at the oil paper interface. The diffusion layer at the oil paper interface would have thus to refer the region where charged ions and polar molecules diffuse from the insulating paper into the oil or vice versa. Driven by the electrostatic forces which are being characterized by the basic differences in chemical potential and concentration of the molecules. So, the phenomenon of diffusion layer at the oil solid insulation interface would have become a dynamic region. Again, I repeat, so the phenomenon of diffusion layer at the oil solid insulation interface would have become a dynamic region where charged ions and polar molecules which are being forced to move between the insulating paper and the oil due to electrochemical potential differences of their molecules. Most important. Both the oil and the cellulose-based paper are being inherently constituted with polar molecules which have the distinct positive and negative ends. Dipoles. However, these polar molecules would have to attract or repel each other, influencing their movement across the interface. As there is always be in physical contact between oil and cellulose-based paper insulation, so there would have an obvious exchange of electrons between them. But because of electrochemical potential differences, there must have some differences in electron affinity of the oil and the cellulose-based paper insulation. The cellulose-based paper insulation as would have lower electron affinity that will lead to accumulate negative charges on its surface, while it is to gain electrons from the oil. Accordingly, the oil would thus to have surplus of positive charges, which diffuse into the oil layer adjacent to the paper. Such discrepancy in electron affinity characteristics would create a distinct boundary with a layer of accumulating of negative charges on the paper surface and a diffusion of positive charges into the oil. The two-layered structure as formed with opposite charges is thus to represent a phenomenon of electrical double layer. Let's stop here. Further to be continued at the later stage. Thank you for listening the video. Kindly do like, share and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section, please. Thank you. Thank you for patient hearing.